before I forget. So welcome everyone. It's my great pleasure to welcome you back to the CMSA Seminar studying for T3 at UNSW. Today we have Matthew Kwan talking here about friendly bisections of random graphs. Matthew did his undergrad at UNSW, then went for PhD at ETH, postdoc at Stanford University, and he is now an assistant professor at the IST Austria just very recently. So it's my great pleasure that you're talking, and the stage is yours.
Thanks, Anita. It's a great pleasure for me to be talking here as well. Thanks for the invitation. Yeah, so I was an undergraduate at UNSW, and during that time, I worked with Catherine Greenhill on random regular graphs, which I now know is a very Australian topic. So I'm very happy to be talking today about a project that uses some of that machinery, like random regular graphs machinery, and I think kind of an unusual way. Anyway, so I'll be talking about friendly bisections of random graphs. It's joint work with Asaf, Bhargav, Ashwin, and Mehtab. And yeah, please feel free to interrupt and ask questions and so forth. I think there will be time for it. Okay. So let's start with some motivation. So let me remind you about cuts in graphs. So a cut is a partition of the vertex set of a graph into two parts, which we'll call A and B. And then the size of the cut is just the number of edges between the two parts. And then a max cut or a maximum cut is just a cut which has the maximum possible size. So that's I mean, those are some very standard definitions. And so here's another definition that's not quite as standard, or at least this name is maybe not quite so standard. But let me say that the friendliness of a vertex with respect to a cut is its number of neighbors in its own side minus the number of neighbors in the opposite side. So it's the number of friends it's connected to minus its number of enemies. Yeah, so if V is in part A, it's the degree into A minus the degree into B, and vice versa if it's in the opposite part. Now here is a classical fact about the max cut, that there can never, in any max cut, be a vertex with positive friendliness. That is to say, every vertex has a friendliness at most 0, and the reason for that is that if there were a vertex with positive friendliness, which had more neighbors on its own side than the other side, then you could just move that vertex to the other side, and that would increase the size of the cut. So you'd increase the number of sort of crossing edges by doing that, and that can't happen in a max cut. So of course that implies that every graph has a so-called unfriendly cut, meaning a cut where every vertex is unfriendly. And obviously, despite the fact that max cut is like a computationally difficult problem, it's really easy to actually find an unfriendly cut in practice. You just repeatedly look for a vertex which is friendly, and if there is one, you move it to the other side. And doing that always increases the size of the cut, so it has to terminate eventually, in which case all the vertices are unfriendly. Yeah. It's important, by the way, that if you make this move, if you move a friendly vertex to the other side, you're not necessarily decreasing the number of friendly vertices. The only guarantee is that you're increasing the size of the cut. So the number of friendly vertices could fluctuate in some funny way. Anyway, that is a fact. Yeah, I suppose I should. I mean, I don't want to say too much about motivation and so on. But this max cut parameter is obviously a very important thing in computer science. It's one of the fundamental NP-complete problems. And somehow finding an unfriendly cut is like a local version of the max cut problem, which is of theoretical interest in computer science and in statistical physics as well for some reason. Okay, so that's what max cut is. There's a few other fundamental types of graph partitioning problems, and perhaps the next one you might think about is the min cut problem, where you ask for a cut of minimum size. And obviously that's a really trivial problem unless you restrict your attention to non-trivial cuts, where you demand that both of the parts are non-empty. Now, in many ways, min cut is a much simpler problem than max cut. I mean, there's a polynomial time algorithm for computing the min cut. But one aspect in which it is not simpler is that we don't have a similar type of local property. So it is not in general true that a minimum cut or the minimum cut or any minimum cut is friendly. And the reason for this is basically just that we don't allow the cut to be trivial. So if one of your two parts consisted of a single really unfriendly vertex, you're not allowed to move that to the other side to make the cut smaller. Yeah, and actually, besides the min cut, there are graphs which have no cut at all, in which every vertex is friendly. So the property of having a friendly cut is a bit more interesting than the property of having an unfriendly cut. Actually, it's NP complete to decide whether a graph has any friendly cut. But there are some very nice theorems in this area, sort of in this direction. Perhaps the most famous one is a theorem of Stiebitz's, which answered a question of Carson Thomason, which says there is always a cut which is very nearly friendly. So each vertex has friendliness at least -1. Yeah, so actually he proved something a little bit stronger than this, but maybe let's not worry about that. So on the one hand, you can always find an almost friendly cut. And the counterpart of that is this beautiful conjecture, I think, of Barn-Lineal, which says that you can almost always find a genuinely friendly cut. So they conjecture that for every D, there are only finitely many D regular graphs which do not have a friendly cut. And there's some work in this kind of direction, where almost all is in the random sense, by Lineal and Lewis, who proved that almost every regular graph has a friendly cut. Okay, so that's a quick summary of friendly and unfriendly cuts. So friendly cuts are a bit harder to think about than unfriendly cuts, but we can mostly guarantee friendly cuts in various senses, and sort of we understand more or less what is going on. Okay, so now let's talk about bisections. So we've talked about max cut and min cut, and the other sort of fundamental graph positioning problems are max bisection and min bisection. So what a bisection is just a cut where the two parts have exactly equal size. So for that, I need the number of vertices to be even. And so let's just, you can make a similar definition if the number of vertices is odd, but let's not worry about that. And so then the min bisection or the max bisection problem is trying to minimize or maximize the size of a bisection, obviously. And so these are both NP complete problems, and actually they're equivalent problems, unlike min cut and max cut, because a min bisection of a graph is the same as a max bisection of its complement. So these are really the same problem. And so now, just like for max cut and min cut, you can ask for some local optimality properties. So you can ask, can you find a friendly bisection or an unfriendly bisection? And it turns out this is, the bisections setting is much more difficult than the general cut setting. And there's very little that is known in this area. But there is an old conjecture due to Furedi, which says that almost every graph has a bisection in which almost all vertices are unfriendly. So obviously the formal way you would like to say this is as a conjecture about random graphs. So what Furedi conjectured is that in a random graph GN1/2, where you flip a coin to decide, for each edge whether to put that edge there, or equivalently just a uniformly random n vertex graph. In such a random graph with high probability, there is a bisection where all but little o of n vertices are unfriendly. So all but a vanishingly small proportion of vertices are unfriendly. So he actually asked the friendly version of this problem, but friendly and unfriendly are basically equivalent here if you consider the complement of the graph. It's just a little bit more convenient to talk about unfriendly bisections. Okay, so this is Furedi's conjecture. There's a very basic heuristic why we should expect this to be true, which is perhaps why he conjectured this. So the point is that the total number of bisections that you have to choose between is, well, it's n choose n over 2, which is about 2 to the n. It's about 2 to the n over the square root of n. And if I give you a particular bisection, then each vertex is unfriendly with probability almost exactly a half. So you ask, do I have more neighbors among my friends or my enemies? They both have the same size. Well, they both have almost the same size, so it's about a half. So if you naively assumed that the friendliness of each vertex was independent, then the probability that a given bisection was completely friendly, that every vertex is friendly, would be about 2 to the minus n. And that basically exactly balances with the number of bisections that there are. So if you only ask for an almost friendly bisection, where almost all vertices are friendly or unfriendly, then you would expect there to be exponentially many of them, or some sort of expectation heuristic would lead you to believe this is true. This is really just a heuristic. And I should stress that it's actually extremely difficult to compute the probability of the given bisection has a given number of friendly vertices because you do not have independence here. But the correlations here seem to be working in your favor, because if you know that a vertex is unfriendly, that means it's got more neighbors on the other side. That means those neighbors are in turn more likely to be unfriendly. And so with the positive correlations, this is really a conservative heuristic. So this is probably true. Okay, so that's the conjecture. And together with my co-authors, Asaf, Bhargav, Ashwin, and Mehta, we recently proved Fidedi's conjecture. And in fact, we also, well, as a byproduct, the proof gives an efficient algorithm, an efficient randomized algorithm that actually finds an unfriendly bisection. Okay, are there any questions about any of this? Okay, so that's the introduction. Now I'm going to spend the rest of my time telling you how to prove this theorem. So I think there's a lot of really interesting ideas and techniques here. Okay, so here is the starting point. So remember on the first slide, we proved that if you have a max cut, you can't have a friendly vertex, because if you did, you could just move it to the other side and make the cut larger. Well, you're not allowed to do that in a bisection. I mean, I'm not allowed to just move a vertex to the other side because that would imbalance the bisection. But I can do something very similar, which is just to take a vertex on each side and swap them. So if you have two vertices, one on each side, and they both have positive friendliness, they both have more neighbors on their own side than the other side, then you can swap them with each other. You'll still have a bisection, it'll still be balanced, and you'll have increased the size. So this can't happen with a maximum bisection. So an obvious corollary of this is that in a max bisection, at least half of the vertices are unfriendly. So either all the vertices in A are unfriendly, or all the vertices in B are unfriendly, because otherwise you could do this swap. Yeah. So I mean, if you want to, as sort of an attempt to find an unfriendly bisection, you might start with an arbitrary bisection and repeatedly swap friendly vertices as long as you can. The problem would be that it might be that you run into a situation where I run out of friendly vertices in one part, and at that moment all the vertices in the other part are friendly, and I don't have any power to do any swaps anymore, but I'm nowhere near my goal. And that's really basically why this problem is hard. So the fact that when you consider these kinds of iterative procedures, things get imbalanced in some way. So if you want to try and overcome this, you can try to come up with all sorts of like crazy swapping rules that try to simultaneously increase the size of the cut and keep it balanced. Something that you can iterate and make this sort of thing work. So none of that seems to be effective. At least we certainly weren't able to do anything like that. But one very simple thing that we might try is to use the probabilistic method. So to make every decision randomly, to start with a random bisection and repeatedly swap pairs of friendly vertices. So the idea here would be that, like the reason why the randomness is meaningful here is that, maybe in principle, if you do the swaps in some bad order, you might end up in a really imbalanced situation where, all of A is friendly and all of B is unfriendly. But somehow this feels like kind of a pathological thing to happen, that, if I do the swaps randomly, then it's very likely that things stay roughly balanced. And if the number of friendly vertices on each side stays roughly balanced for the duration of the process, that will mean that you run out of friendly vertices at the same time on both sides, which will tell you that almost all vertices are unfriendly at that point. Yeah. So I guess to summarize that informal observation that I just made there, the key observation here, this is really what gave us hope that this kind of approach could work, is that if you want to consider this, so this is some sort of random process where you repeatedly take a random vertices and swap them. You don't actually need to understand the trajectory of this process. You don't really need to understand what it's doing. All you need to do is show that it concentrates. So to elaborate on that, if I let xt be the number of unfriendly vertices in part A after t swaps, if I can just show that xt is concentrated so that its variance is little over n squared, so that would imply that xt is likely close to its expected value, whatever that expected value is. And by symmetry, the number of unfriendly vertices in B has the same distribution. So it would also be concentrated around that expectation, who knows what that value is. So that is to say, at any given point in time, there are roughly the same number of friendly vertices in A and in B. And that's what you need to prove the theorem. Okay. Yeah, so this symmetry argument is actually very subtle and very sneaky. So as we'll see soon, the evolution of the process is actually extremely delicate. And also, by the way, it doesn't seem to this sort of thing doesn't work for directed graphs, for instance. But we don't actually care about what the trajectory is. We just need concentration. Anyway, so now the task is to show concentration, and that seems like good progress because there are lots of general tools to show concentration. So in case you are not familiar, let's discuss some of the basic things that you might try. Yeah. So perhaps the most general purpose thing that there is for this kind of situation is the F-Runstein inequality, which is some sort of perturbative thing where in order to show a random variable is concentrated, you want to show that it's not too sensitive to fluctuations in the underlying probability space. So the setting is that you have a function of n independent random variables, x1 through xn. So z is the random variable that I'd like to understand. And then I consider the effect of randomly resampling one of the variables xi. So to be precise, you consider the change that you get when you resample xi, and you look at the expected square of this quantity. Then you sum that up over all I, and that's an upper bound on the variance. So as I said, you just need to show that small changes in the underlying random variables typically do not have a big effect on the outcome. And this will tell you that it's concentrated. So for example, if you want to prove that the chromatic number of a random graph is concentrated, or if you want to prove that you have like a random instance of the traveling salesman problem, then the length of the shortest path is concentrated. You can use this kind of inequality. And the crucial thing is that it works even if it's hard to compute the expected value of z. It's sort of a very soft inequality. Yeah. So in our setting, the way that we would want to apply this is that we would want to resample one of the random edges of our graph. So the random variables x1 through xn would be like measuring whether each edge is there in the random graph. So you want to resample an edge and think about what does that do to the behavior of the process. You know, hopefully if you only change one edge, then the process typically doesn't get changed very much. It typically runs in basically the same way. So I think given what I've said so far, this seems like kind of a natural thing to try. It seemed at the time like one of a small number of things that even make sense to try. And actually it's pretty close to working. But we were not able to make it work. Somehow you need to rule out the possibility that you just change a single edge and it has this huge cascading effect and completely changes the results of the process. And it's sort of I mean, I don't believe that this is likely. So I don't believe there's like a fundamental obstruction to this, but actually understanding this kind of event seems about as difficult as understanding the process to begin with. So that's no good, which is a shame because this is like the softest thing you can try. Okay, but there are some other standard things you can try as well. Perhaps the next most obvious thing is a differential equations method. Let me, in case you may not have heard of this, let me very quickly sketch the idea. It's a very general and powerful way to study all sorts of combinatorial random processes. So the way that it works is that you have some kind of combinatorial random process and you want to find an ensemble of random variables that evolve with the process and sort of track the statistics of how the process evolves. And the critical thing you want this ensemble to satisfy is that the expected change in each random variable, so the expected change of that random variable at a given step, that change can be approximated in terms of the variables in my ensemble. So you can view the whole thing as like a system of differential equations. Well, it's somehow approximated by a system of differential equations where the expected change in something is measured by the current status of all the things. So you can solve some system of differential equations, get some like guess or some ansatz for the trajectory of the process, by integrating the differential equations, and then you just need to show that the process is likely to actually follow that trajectory. And usually that's pretty easy with some martingale concentration inequality. So you look at the process minus the guess. That's approximately a martingale, blah blah blah, and it's concentrated. Yeah. So this is the differential equations method. It's definitely a less soft thing than F von Stein. You usually have to do a lot of calculation to make this work. But it works for all sorts of situations. Can we do it here? Unfortunately, as far as I can tell, no, this is also not appropriate here. So somehow this is just the wrong sort of process for this sort of method. So maybe a first instinct would be that I would record for each vertex how friendly that vertex is at any given point in time. And so these collection of friendliness random variables would be my ensemble of random variables. But this is clearly useless because, I mean, if you're interested in concentration of these random variables, they're just concentrated around 0. I mean, the friendliness of every vertex is typically around 0, and it's only the fluctuations within the window of concentration that are sort of driving the process. So there's no meaningful sense in which you can say that, you know, the friendliness random variable is concentrated around something which tells me what's going to happen at the next step. Like, you really need to understand what's happening within the window of concentration. So that's no good. A second thing you could try to do is track some kind of aggregate statistic. Like, maybe I want to track like the number of friendly vertices or something instead of the friendliness of each vertex. But this kind of information is just way too little information to predict what's going to happen at the next step. So you really need to know the entire distribution of how friendly every vertex is to be able to predict what's happening at the next step. And it's very difficult to imagine how to summarize that into some random variables that evolve according to some differential equation. So this is no good, but this is getting a little bit closer to what we actually did do and what did work in our actual proof. So let me now stop telling you about things that don't work and start telling you about some things that we were able to use. So a first thing that you can observe, and is actually quite crucial, is that this process, and actually many processes, many different kinds of combinatorial processes, become much simpler if you nibble them. So what I mean by that is that the way I've defined the process so far is that, you know, at each step I'm swapping a pair of vertices in a way that depends on the entire history of the process. And I'm doing that many, many times. So instead of doing that, I can do a small number of big swaps, where in each big swap, I swap a large number of random vertices all at once. So the reason that you can do this is the lemma on this slide, which says that in every bisection, there are not too many vertices with friendliness extremely close to 0. So almost all of the vertices have the absolute value of their friendliness being about the square root of n. And so the reason this is true is that there are only 2 to the n bisections, well, at most 2 to the n bisections. So anything that happens with super exponentially small probability, just with high probability, never happens for any bisection. Now, for each vertex, its friendliness, so its number of vertices in part A minus its number of vertices in part B, it's basically a Gaussian random variable. Its standard deviation is square root n. So it's very unlikely that you'll see a deviation smaller than c times square root n for small c. As c goes to 0, this probability goes to 0. And so the probability that this happens for many vertices at once, well, if c goes to 0, then the probability that happens for linearly many vertices is super exponentially small. So just a union bound will show you that this never happens for any bisection. So all bisections have the property that all vertices have like significant friendliness. And the upshot of that is that if I swap a lot of friendly vertices at once, they can't all have friendliness close to 0. Like, a large number of them have to have large friendliness. So if I do one of these swaps, like if I swap many vertices at once, that increases the size of the cut by rather a lot. So before, if I swapped a single pair of vertices, I would increase the size of the cut by at least 1. Now, every time I do one of these big swaps, I'm making some enormous effect on the size of the cut. So you need to do some calculation to see what exactly you get from this. But it turns out that if you repeatedly swap epsilon n friendly vertices at once, which you're allowed to do because we're interested in going until there's, you know, epsilon n vertices left, which are friendly. If I do that, then this can only go on for about e to the 1 over epsilon steps before the friendliness would get, the size of the cut would get impossibly big. Yeah. So meaning after that many steps, you'll reach a point where almost all of the vertices on at least one side are unfriendly. And again, we want to show that things are balanced to show that, in fact, almost all vertices in the entire graph are unfriendly. Okay, so yeah, we still have this highly dependent process that we don't know how to understand, but now I only need to understand this process for a constant number of steps. So if I want to find a 99% unfriendly bisection, maybe I need to track this process for 1,000,000 steps or something. And that the fact that it's now a constant number means that we're not fighting for parameters to fight against each other, and that this makes everything much simpler. Okay, so that's one idea. A second important idea is that instead of exposing the random graph all at once, I want to expose information gradually as I execute the swapping process. Meaning I don't even want to expose what the graph is until I need to know that information. So meaning that at each step we don't just have the randomness of the random swap, we also have some randomness coming from the random graph itself that we hadn't exposed yet. And so this extra randomness is super helpful in establishing concentration. So to be more specific about that, so the way the process works is that so at each step I want to swap some friendly vertices, and so in order to know how friendly a vertex is, I need to know its degree into A and its degree into B. So what you do is you just reveal that degree information, but you do not reveal any other information about your graph. So meaning, for each vertex I reveal the size of its neighborhood in A and the size of its neighborhood in B for whatever A and B are at that point in time. But I do not reveal what those neighbors actually are, only the number of them. So, now that you've revealed some kind of partial information about your graph, now your random graph has some conditional probability distribution. Namely, it's a random graph where I've conditioned on, every vertex having a particular degree into a particular set or something like that. Now, it's certainly not, yeah.
So if you do that and you expose your random graph one at a time, then you can just start with any bisection at the beginning, right? Like what you said at the beginning, you take a random one, that's just void.
That's right. Yeah, so by symmetry, yeah, any bisection will do. Very good. Yeah, so this kind of situation where you've got a random graph in which you've conditioned on certain vertices having certain degrees into certain sets, this seems like a completely intractable, at least maybe naively, it sounds like a completely intractable thing to get a handle on, because the way you study random graphs is, every edge is a coin flip, so they're independent, so you multiply probabilities, and you just can't do that anymore in this conditional situation. But it's actually known that random graphs with constrained degrees behave sort of on a large scale in basically the same way as ordinary random graphs. Of course, all the statistics are biased in some non-trivial way because of the degree constraints, but you have the same sort of like concentration behavior, or any kind of large-scale behavior is about the same. So how do you actually study these things? Well, it's really hard, but the theory here has already been developed. Yeah, I think the original ideas I think are due to McKay and Wormold, and there are extensions that we need due to Canfield, Greenhill, and McKay. So it turns out that the way that you study these things, constrained degree random graphs, is by defining generating functions in a large number of variables, so that the coefficients of the generating functions record the numbers that you're interested in, and then you do some high dimensional complex contour integrals to actually extract these the asymptotic values of these coefficients. And so if you can count things, you can compute probabilities, and that's what you do. So it's really quite amazing that you can do this, but you can, and so we have some way of getting our hands on constrained degree random graphs. So that's the principle here is that having a constrained degree random graph is essentially as good as having a fresh random graph from the point of view of showing things are concentrated. Okay, so to summarize what's happened so far, so yeah, so at each step we only expose the relevant degree information. So I have to do this a constant number of times, expose the relevant degree information, and then I have a fresh random graph to use to establish concentration at that step. I just need to do this a constant number of times, and then that's the proof. Okay, so that's the situation. So now we need to decide what we are going to track as the process runs that will allow us to get concentration at a given step, given concentration at the previous step. And basically the only way that we are able to make this work is by keeping track of the entire distribution of degrees at each step, which is a very unusual thing to do for these kinds of processes. Usually the goal is to find some sort of summary statistic, like you might want to track the degrees or the co-degrees or something, but here we just track everything. So let me try and be a bit more precise about what I mean here. So for each vertex, I want to record like a log of which side that vertex has been on at each point in the process. So, after k steps, there are 2 to the k possible logs you could have, 2 to the k sequences like A, B, A, B, as I move between the 2 parts according to the swapping process. So you partition the vertex set into 2 to the k parts, depending on the different logs that they have. And then, so after k steps, the information that you've revealed so far is that I know the degree of every vertex into every part. So at the next step, I'm conditioning on this degree information and then working on it with a degree constrained random graph. So what I'm going to record is the empirical distribution of vertices, of degrees of vertices into each part. So how many vertices have a given degree in a given part? So this is a 2 to the k dimensional probability distribution. So, for every part, there's some, the vertices have a distribution of degrees into that part. And then what you're going to show is that the entire empirical degree distribution concentrates around some ideal distribution. So instead of showing that, the number of friendly vertices concentrates around its expectation, I'm showing the entire distribution of degrees concentrates around some sort of more abstract distribution. Yeah. So this ideal distribution is going to look something like a multivariate Gaussian distribution, but it's not going to quite be that because you're twisting things by constraining the degrees. Okay. So you've got some ideal distribution. The empirical distribution is close to that with respect to some metric on probability distributions. So I don't think the metric is terribly important, but for example, the Kolmogorov metric is what we used. So to show that the distribution function, the distribution function of the ideal distribution is close to the distribution function of the empirical distribution. So maybe to give you an example of this. So at the first step, before you've done any swaps, you only have 2 parts. So you've got A and B, and you've got the degree into A and the degree into B. And then that's going to be asymptotically a bivariate normal distribution. So it's binomial into A and binomial into B. That's the Gaussian distribution. After 2 steps, you're going to have a 4-dimensional probability distribution because you've got A in step 1, B in step 2, B in step 1, A in step, and so on. And it's going to look, it's going to be some sort of twisted Gaussian thing where the exact twist would come out of the formulas from this constrained degree random graph stuff. Okay, very good. So the reason we need to track so much information is that you really do need to know the entire empirical degree distribution if I want to be able to understand the distribution at the next step. Like understanding the distribution, so I need to understand the distribution of the degree of a vertex to understand, how likely it is to have a certain friendliness, and to do that, I need to understand this entire distribution. Okay, so now we know what to track and we have a way to track it. So in principle, we could use this machinery of McKay and Wormald and Canfield, Greenhill, and McKay to give a very, very complicated combinatorial sum that expresses the typical empirical degree distribution in step k. Like everything is in principle computable. But it's just, frankly, completely impossible to work with these expressions directly. It's like compounded, it's like sums of formulas which arise from these. Nothing has a closed form. It's a complete disaster, and I don't know how to do this. So our final idea is that, so that would be what you would have to do if you actually want to understand the trajectory of the process and you want to understand what is happening at each step. But we don't care about that. All we want is concentration. So it would be nice if it was enough concentration at step k to imply concentration at step k plus 1 in some black box way. It's not quite as simple as that, but you just need to maintain a little bit more information that you can sort of carry along inductively as you continue the process. So on this slide, I've written what exactly you need to maintain. So the first condition is just a technical thing. If I want to use these enumeration estimates of McKay and Wormald, I need to assume my partition is far from being degenerate. So all of the 2 to the k parts are at least of linear size. The second thing is sort of the main point. You need to show that there is some ideal distribution LK such that the empirical distribution concentrates around LK according to some metric on distributions. But in order to make this induction work, you need two more things. So it's not enough just for there to be some distribution. You need that distribution to be somehow regular. So the first thing is that the distribution cannot be too spiky. So I'm not allowing my distribution to have like a very large probability mass on a single point. It's an anti-concentration condition. And then you also need the tails to not be too fat. So the technical term being that the tails are sub-Gaussian. Yeah, so as I said, it's always going to be something you get by taking a Gaussian and then sort of twisting it in some way. And it's always going to have the same concentration behavior. Like the tail is always going to decay at the Gaussian type of rate. So this is what you need well, if you have these properties, if you have all these four properties, then you can maintain, then these properties hold at the next step. So if all these four properties hold at step k, then they also hold at step k plus 1. And here it's really fortunate that we only have to do this a constant number of times because there's so many sources of error here. It's like that each of these things has some error term, and you're taking the square root of the error term at each step is essentially what's happening. Or I mean, at least. And so it would only be possible to run this sort of thing like for like log n steps before the error terms start to blow up. But luckily, that's enough. Anyway, so that's all I really have to say about the proof. So it's really quite an unusual way to show concentration of a random combinatoric process by exposing only limited degree information about your random graph at each step, and then using these enumeration estimates, these constrained degree enumeration estimates for graphs with given degree sequence at each step, and moreover keeping track of the entire empirical distribution of what's happening in the process, and not just trying to summarize things in some small ensemble of random variables. Okay. So let me finish with some further directions that I think would be interesting. So the first thing is that we worked really hard to establish concentration. That was sort of the point. And I would be really interested if there was some softer way to do this. So really this is kind of a formidable paper. And if there was some way to make F1 work, or, I mean, there are certain other simple information processes that you do have access to. I mean, it's not out of the question that there's some really simple proof that just completely non-constructively shows concentration, and that would be nice. A second thing is that, what our main result is that you can find a bisection where almost all of the vertices are unfriendly. But what if I want a bisection where all of the vertices are unfriendly? So my co-author Mehta did some computer experiments, and if you consider this, we have this. I mean, if you use the vertex by vertex swapping process, where you look for a pair of friendly vertices and you swap them to make it more unfriendly. So that's not going to give you a completely friendly bisection empirically. But if in addition you add some random swaps to sort of get out of local optima that you might fall into. So maybe I think they call this like simulated annealing or something in optimization. But it seems empirically that actually does give you a 100% friendly bisection, and I think it would be really interesting to prove that. So that's an interesting open problem. A third thing is that so we've proved a theorem about random graphs, about almost all graphs, and really it would be very nice to prove something about arbitrary graphs, or at least graphs with some like explicit conditions instead of just being a random graph. Because here we haven't, like often when you prove something about random graphs, you're really proving something about like quasi-random graphs. You're using some sort of, deterministic properties of your graph. But here, the way that we're exposing information, we're really fundamentally using the randomness of the graph. So Balabash and Scott conjectured that in any graph at all, you can always find a bisection where every vertex has friendliness at most 1. This is like the counterpart of Stieglitz's theorem. And that's probably really hard, but yeah, I would be really interested even if you could give me some kind of deterministic property that a large class of graphs satisfy, and which and which have an almost friendly or an almost unfriendly bisection. So even for quasi-random graphs, I think this would be very interesting. And maybe you can even use the same random process that I described today, where you just repeatedly take random friendly vertices and swap them. But if the graph isn't random, then I don't know how to analyze this process. Okay. And finally, I think that the ideas in our proof are of more general interest. And I would like to see more applications of these ideas. For example, two of my co-authors, Ashwin and Mehta, have since used these ideas to study majority dynamics in random graphs and to resolve some conjectures in this area. So majority dynamics is some similar kind of dynamic swapping algorithm defined in terms of degrees. It's supposed to model people changing their mind in voting or something. But yeah, it seems to be a widely applicable type of. I hope there'll be more applications of these ideas. That's the end of my talk.
Well, thank you so much. Let's all unmute ourselves and give a round of applause. And if you have any questions, just unmute or post in the chat, and I can read it out. Feel free to unmute yourself and ask a question.
So a vertex with friendliness 0 is both friendly and unfriendly, right? It's sort of neutral.
Oh, I suppose I was intentionally a little bit vague about this.
Yeah. So I think your friendly bisections are not unfriendly bisections.
Yeah. So one can make a choice here for what this means, but in the setting of random graphs, so for the main theorem that I've been telling you about today, it actually makes very little difference. And the reason is that, there was this lemma. What was it?
Small deviations are rare, or something. Or
small
values are rare.
Yeah.
Right.
So if almost all the vertices are friendly, in fact, almost all the vertices are very friendly, because there's not that many vertices which can have friendliness close to 0. Yeah.
It's like polarized discussions or something, like tribes on social media.
Yeah, there's a vanishingly small proportion of people who
are reasonable. And the thing that your inductive hypotheses that make your argument work with the concentration and the fact that the LK has to be anti-concentrated, I guess does that start to die if you have too many steps as well? I suppose everything starts to fail.
Everything.
Yeah.
I think, anti-concentration is one example. Really everything. I think that probably the way that we control distributions is we divide things up into boxes and we show that the probability mass in each box is about right. And we coarsen the partition into boxes at each step in a sort of a pretty destructive way. And so this is probably the most serious thing that will prevent you from doing this for too many steps. So I suppose one other interesting open problem that I did not mention at the end was, can you still prove something even if you don't nibble the process? So if I actually want to understand the process where I swap a pair of friendly vertices at each step, depending on the entire history of the process, can I show anything about that? Would be interesting.
Thanks.
So you said you're using randomness heavily. You can't, not just pseudo-random properties. What if I change the p from 1/2 to 1/4? Would that? Could you?
Yeah. So I think.
Does the question even make sense? I don't know.
So yeah, it absolutely makes sense for any p. So for constant p, I think. I mean, for p bounded away from 0 and 1, I think it's really the same question. Our proof works, and I don't know any proof that works there that doesn't also work for the p equals 1/2 case.
Mm-hmm.
When you're talking about very sparse graphs, it's possible that something different can happen. And when you're talking about very, very sparse graphs, certainly one can do things. So certainly our method is going to break down when you get sparser, but then I think when you get very sparse, the structure of the graph is like, I'm not sure, but it's interesting for all p, I think.
Okay. And you said for constant P, your proof would probably just go through.
Yeah, I'm sure it would go. In fact, the Ashwin method had to work out general P versions of everything for the majority of that dynamics paper anyway. So,
I see.
so I mean, it's not written up, but I'm quite confident that it just works.
Yeah. Okay, are there any other questions from the audience? That doesn't seem to be the case. So let's thank Matt again by unmuting and uploading. Thank you. And I'll stop the recording.